Hi folks, so in this video we're going to have a look at how we can integrate more complex fractions like this one that we can see on the screen. Now at the moment this is a big mega fraction. We've got parts on the top line that's linear, a part on the bottom line that is a quadratic, and we don't have a anti-differentiation quotient rule or anything like that that we can use. We've looked at using substitution in previous lessons, and there's not an easy or obvious value that I could substitute into this equation. So what we use for this type of problem is a method that's called integration via partial fractions. So before we think about what a partial fraction is, the easiest way to explain that is let's look at the problem if we had the fraction 2 over x minus 2 plus 1 over x minus 3. Now at the moment, if I wanted to integrate both of these fractions, that would be really easy. I could split it up, and they are both log problems. So this one on the left would be 2 log e of x minus 2. And the one on the right would be just log e of x minus 3. So that's all quite nice and easy. But my fraction over here doesn't look like that. My fraction hasn't got two parts on the bottom. It's got a quadratic. Okay, so our goal for this video and our goal for partial fractions is to actually just change the quadratic fraction, our big mega fraction over here, into something that's much simpler like this. So let's have a little bit of a look and a think about. Again, let's start with this problem over here. Let's think about what would happen if I got a common denominator for this problem. Okay, so if we have 2 over x minus 2 plus 1 over x minus 3. If I wanted to add these fractions together, I'd have to get a common denominator first. So to get that common denominator, I am going to multiply the left-hand fraction by x minus 3 on the top and x minus 3 on the bottom. And for my right-hand fraction, I'm going to multiply that by x minus 2 on the top and x minus 2 on the denominator. So what we've created here is a common denominator. And if we have that common denominator, we can now actually just put my fractions together over the same denominator, like so. And then with some tidying up and expanding, it looks like this. And you can see what I'm actually creating here is a very similar problem to my mega fraction that I had at the beginning. So to integrate this, we want to go from this difficult version back up to a simplified version like that. So we're going to do exactly what we just did with getting a common denominator, only in reverse. And that's what partial fractions is. Okay, so how do we actually start? Well, the first thing I'm going to do to start here is I'm going to find out, are there two linear factors on my bottom line? And I can factorise the denominator in this case by looking for two numbers that multiply to equal -3 and the same two numbers that add to equal 2. So just my quadratic factorisation techniques. And that's going to be x plus 3, x minus 1. Okay, so looking at my problem that I had down here, I've sort of got this point now where I've separated the denominator into two linear factors. And I want to try and go back to this space like this. So I've got the 2 over x minus 2 and 1 over x minus 3. So what I'm going to recognise, or what I'm going to think about, is I'm going to say, well, I've got my 5x plus 7 over x plus 3, x minus 1, I'm going to assume that there can be some value that I can put over x plus 3 and some value that I can put over x minus 1 that would be equivalent to this mega fraction. So I'm actually just creating two separate fractions by using these linear factors on the bottom line. Now, if I can work out what a and b is, then I'm sorted. I've actually got my two easy fractions. And that's exactly what we're going to do now. We're going to solve this problem to find out what a is and this problem to find out what b is. So how do I do that? Well, I start by working out what this would be if I went back to a common denominator now. So if I wrote that problem as a over x plus 3 plus b over x minus 1, if I multiply both the denominator and the numerator by x minus 1, I'm creating the common denominator of x plus 3, x minus 1. And on the right hand side, if I multiply the denominator by x plus 3 and also multiply the numerator by x plus 3, I've set up my expression so I now have this common denominator of x plus 3, x minus 1. So these two expressions have to be equivalent. This must be equivalent to this, and it must be equivalent to this. All right, let's put all of that together. We can say that 5x plus 7 divided by x plus 3, x minus 1 must be equivalent to a times x minus 1 plus b times x plus 3, all divided by x plus 3, x minus 1. And because both of our denominators are equivalent, I can then go one step further and say that 5x plus 7 must be equivalent to a times x minus 1 plus b times x plus 3. And we're starting to get to this space where we have an a and a b, and we only have one equation though. So I'm kind of a little bit stuck, where normally when we've got two unknowns, we use two equations to solve them simultaneously. In this particular case though, because the x's on the left-hand side are the same as the x on the right-hand side, this is like a polynomial that we're trying to solve. And it doesn't matter what x is, the left-hand side will always be equal to the right-hand side. So we can choose any x that we want to help us solve this problem. And in this particular case, what I can do is I can actually choose a specific x that helps me. Let's say x is equal to 1. Now if I choose x being equal to 1, my expression ends up looking like 5 times 1 plus 7 on the left hand side. On the right hand side I get a times 1 minus 1 plus b times 1 plus 3. Now the bonus of choosing 1 for x is that this first part of the expression that's got an a attached to it, that'll just cancel out. It'll equal 0. So by selecting x equals 1, on the left hand side my equation becomes 12. 5 plus 7 is 12. The a value disappears and I get 4b. So from here I find that 4b equals 3. Sweet. We have just actually found out the numerator for one of my fractions. We can keep going now, and we're going to repeat exactly that process, except now I'm going to let x equal negative 3 to cancel out the b part in my expression. So that looks like this. I end up with 5 times negative 3 plus 7 equals a times negative 3 minus 1 plus b times negative 3 plus 3. So same thing again, the b part here, it cancels out, which is really, really handy because my expression then only has one unknown, which is a, and I can solve for one unknown. So on my left-hand side, I've got minus 15 plus 7, which is 8. On my right-hand side, I get negative 4a, and then a little bit of solving, and I get a equals negative 2. Awesome. We now have my b value and my a value that creates an equivalent expression for my original integral. Okay, so got to try and remember all of those numbers now. So I can write that 5x plus 7, so therefore 5x plus 7 divided by x plus 3, x minus 1 is equivalent to a over x plus 3. Now we know a is negative 2 plus b, which is 3, over x minus 1. So these two expressions must be equivalent. So therefore, the integral of 5x plus 7 must over x plus 3, x minus 1 dx must be equivalent to the integral of negative 2 over x plus 3 plus 3 over x minus 1. And this new integral expression is really easy to integrate. It becomes negative 2 log e of x plus 3 plus 3 times log e of x minus 1. And then, of course, our constant of integration plus c on the end. So partial fractions is a technique that allows us to integrate more complex and complicated integral problems involving fractions.